Good evening, dear friends. Today I am going to speak about what is called the Darboux's theorem. This is called the Darboux's intermediate value theorem for derivatives. You have all heard about the intermediate value theorem for continuous functions that is actually credited to the famous mathematician and a Czech priest, a priest from Prague called Bernard Bolzano. And it's one of the greatest theorems of calculus or analysis, whatever you want to say. If f is a continuous function from an closed interval a b to r, and if f dash a is strictly less than 0 and f dash b is strictly bigger than 0, means they have opposite signs. You could choose the other way also, f dash a to be strictly bigger than 0 and f dash b to be strictly less than 0, doesn't matter. Then there exists a c, a number which is lying between a and b in the open interval a b, for which f dash c is equal to 0. Which simply means that, okay, if you have something like this, AB, so if f dash a is say less than 0 and f dash b is greater than 0, so a continuous function like this, basically, then there will be a point C. So here is a railway line crossing, there's a road from village A to village B. So then the road, if the village A lies on one side of the railway line and the village B lies on the other side of the railway line, then there must be a point where the railway line must be crossed by the road. That's the whole idea. Now here we require the function f to be continuous. What Darboux theorem says is that take a function ab in R, from function ab to R, right, a real valued function, and assume that f is differentiable on the open interval ab, and the right derivative of f exists at a and the left derivative of f exists at b, because there is no other choice here, because derivative needs both ways, even continuity needs both ways. So whenever, if you say a function continuous on the closed interval ab, at the end points you are essentially talking about right and left continuity. So on the A side, you are talking about right continuity. On the B side, you are talking about left continuity. Here also, we are talking about the left and right derivatives. Okay. So if they exist finitely, if f dash a is strictly less than 0 and if f dash b is strictly greater than 0, then there must be a c in ab such that f dash c is equal to 0. Okay. So this is the right derivative at a, f dash a, and this is the right derivative at a, and then this is the right derivative, left derivative at b. So let us first do the proof and then see. Here we do not assume the continuity of the derivative. It's an important thing to remember, and you understand calculus much better if you understand the derivative of a function. Derivative of a function need not be continuous. If a function is differentiable, the function is continuous. But that doesn't mean that the derivative itself would be continuous. We'll give an example at the end, but let us just go through the proof. Now, by the hypothesis that we have taken that this left and right derivative exists at the end point and it is differentiable in the interior part in the open interval AB, that allows us to prove that f is continuous on AB with the left and right part being the left continuity and right continuity at the end points A and B. So, by the famous Weierstrass theorem, f is bounded on AB. You know this fact. And the bounds are attained. So, which means there exists an x, it means there is a maximum value and a minimum value, and there are points at which these values are attained, points within AB. So, we will just take the minimizing value. We are choosing the minimizing value because of the sign that we have chosen. If it was a different sign, we would have chosen the maximizing value. So it's bounded on AB and the bounds are attained. So there must be an x in AB such that fx is less than or equal to fy for every y in AB, right? That's the minimizing value. So I do not now know where A and B lies. So if I do not know where this x lies. So suppose x could be A, x could be B, or x could be something in between. So if x is equal to A, then I leave it to the reader, and it's very simple to show that the right derivative at A must be greater than or equal to 0. So the right derivative at A is simply this. If you forget, its h has to be positive because you can move only on the right side. H tends to 0 plus. So this is the definition of the right derivative, and you can immediately figure out that why that the right derivative would be positive, right? So the right derivative should, sorry, not positive, non-negative, because this upper part is greater than equal to 0. This part is greater than equal to 0, and h is positive. So now f dash h strictly less than 0, so it cannot be obviously the minimizer. Similarly for b, because if b is the minimizer, then f dash, the left hand derivative at b should be less than equal to 0, which is a contradiction from the hypothesis, because f dash minus b is strictly bigger than 0. So there must be a c in ab, which is a minimizer of f over the whole interval ab, not closed open interval, but the whole closed interval ab. And I leave it to the viewer to prove, because now it is in the interior point, that f dash c is equal to 0. It is very simple to prove that f dash c is equal to 0. Okay. So there ends my Darboux theorem. There is no requirement of continuity on the derivative. So here is an example. F is differentiable but f dash not continuous everywhere. So this is the famous example, and this is a prototype example you'll find in many books. So let us take f from one 0 to sorry what I am making. So 0 0 1 to r. Let me define it as f of x is equal to x square sine x square sine 1 by x, when x is not 0 but anything between 0 and 1 including 1, and is equal to 0 if x is equal to 0, because here there will be a discontinuity at 0, because, and this is a removable discontinuity, because the limit of x square by sine x as x tends to 0 is 0. So you define f0 as 0. So this is a continuous function. F is continuous at x equal to 0 by definition, and also at other points. Now let us find the derivative at 0. The derivative at 0 is limit h tends to 0 h square sine 1 by h minus 0 by h, which is h, which is h, which is nothing but h sine 1 by h, because you cancel the h. Now limit as h tends to 0 h sine 1 by h is 0. I'll not prove it to you because this is a simple thing, because sine 1 by h is a bounded function between 0 and 1, and h is going to 0. So if you multiply that with a bounded function, so both sides the limit would be 0. And so basically it's like this. If you want to make a proof, then it is h sine 1 by h. Suppose h is positive, it can be written as h minus h if h is positive. So take the limit on both sides is 0. So limit h sine by 1 h is 0 when h is positive. For the negative part, you can do it yourself, but this is the result. Right? So now what happens? I know the derivative at 0 is 0. So f dash 0 is 0. At any other x other than 0, that is when x is not equal to 0, and between this is in this part, then this is equal to, let us do the simple differentiation, sine 1 by x plus x square cos 1 by x and now you take the derivative of cos x, which is minus 1 by x square. So what we have is 2x sine 1 by x plus cos 1 by x, minus cos 1 by x. Now the limit of f dash x as x tends to 0 is 0 minus limit, if it at all exists, it should be like this, because this limit would be 0, because sine 1 by x is bounded again. But this thing does not exist. This limit does not exist because cos 1 by x keeps on oscillating between 0 and 1, 0 and 1 cos. So it just keeps on oscillating heavily. Not, so it this function oscillates, right? So does not go to any limit. So which means that f dash x, f dash as a function is not continuous at x equal to 0. It's continuous at other points. So a function which is continuous in the whole interval 0, 1, including 0 and 1, is differentiable on the whole interval 0, 1, but the derivative is not continuous at x equal to 0. So I hope you enjoyed this little discussion where this is a very powerful result of Darboux. Darboux's name I hope you know. Gaston Darboux is famous for giving a different approach to Riemann integral. The upper Riemann sum and the lower Riemann sum that you learned in your calculus course is due to Gaston Darboux. Riemann didn't take this upper and lower Riemann sum approach. So here is a nice thing, because we do not assume the continuity of the derivative. In fact, for such functions also, the intermediate value theorem actually works, and that's kind of amazing. That you don't need the continuity of the derivative. Thank you very much.